Hello and welcome back to Precalculus. We are going to talk about transformations of functions. We're going to shift functions left, right, up, down. We're going to reflect them on x and y axis and see if we can stretch them and shrink them and do all of these cool things. Now, there is direct relation, obviously, between the way the function is written and the transformation that you are performing. So our goal is to discover all of those in this one section. There's going to be a lot of them, obviously. So let's first, before we go into any of those, put some basic functions on the screen here. So constant function y equals c. That is going to be just a horizontal line on y-axis through C. Now, when you look at this one, right, shifting in left and right makes no sense. I mean, you can shift it left, but you're not going to see anything. So only technically shifting it up and down makes sense. And also reflecting on x-axis, reflection on y-axis makes no sense because it's going to be, again, the same function. So when you see a line of some kind, you ask yourself, well, what kind of transformation will actually change change what I see, and then you go from there. You have your linear function. That's your good old y equal mx plus b. You know this one from algebra. You beat it to death over there with your x-intercepts and y-intercepts and slopes and positive, negative slopes, parallel slopes, perpendicular slopes, points and all of that stuff. It's just a linear line, right? And then you have your quadratic. Which is good old y equal just x squared. We can just have the basic one, but technically it's ax squared plus bx plus c, spanning a lot more. And then you have, I'm just going to say more on polynomials in chapter 2. Your entire polynomial is just to learn polynomials. So we're not going to get excited with the cubic and the fourth power and fifth and so on. And we're going to see all of that in chapter 2, so let's not dwell on it right now. So more on polynomials in chapter 2. Radical, y equals square root of x is the basic one. You are memorizing the basic functions, the basic shapes, and then you will see that you use those to graph more complicated stuff. So if you don't know these basic shapes, you technically are paralyzed. You can't do anything else. You have to cheat with your calculator every time. But if you transfer to a school that has a zero calculator policy, like Rutgers, NGIT, and so on, where you are not allowed to use calculator at any time, not exams, homework, or anything, then obviously you can't do any of this stuff. So that's a radical. Rational, y equals 1 over x. So these are all basic shapes that you are supposed to know for now. And one more, absolute value, haha. And that's just this v. There we go. So these are the basic shapes, and now we're going to see what we can do with these functions. So let's start our transformations. Shift, up, down. That's the first one. If you want to shift the function up or down, you are going to add or subtract a number to the entire function. This is actually the formula. So you have your, what you would call a vanilla function, right? The default function, which is one of these shapes. And then you just add or subtract a number to shift that function up or down on axis, y-axis. So let's say that f of x is equal to square root of x. Okay, then f of x equals square root of x plus 3 is going to have the graph which is shifted 3 units up, because plus 3 is 3 up, because plus 3. Now you go and say, okay, the old graph, which is this dotted, right? We know that's the default, the vanilla graph, if you want to call it vanilla graph. That's this. Now, that's something that you learned, right? It's not communicated to you in your dream. You learn the shape of the basic graph. And if you are questioning any of these shapes, well, go ahead, pick your x's, compute your y's, get your points across, and plot and verify each one of these graphs. By the end of our course, we will add to this logarithmic, exponential, and 6 trigonometric graphs, and maybe a couple of inverse trigonometric graphs. We're going to more than double this list by the end of the course. Then you will keep building this as you go through your calculus. So when I have to solve a problem to graph root x plus 3, I have to know what the original graph looks like. And then I go and I say, okay, this point where the graph kind of starts goes 1, 2, 3 units up, and here is my version. This is root x plus 3. The one on the bottom is just root x. So the graph keeps the same shape. It's just every point is shifted 3 units up. Similarly, if you have, let's say, g of x is equal to, I don't know, 1 over x, for instance, and you want to take a look at new function g of x is 1 over x minus 2. Same thing happens as before. You can draw on your xy plane your vanilla graph. So this is your vanilla graph, the one that you memorized. You just know what 1 over x looks like. Clearly, and I have to use that word. I know many of you don't like when I say clearly in mathematics and it's not clear, but this is clear. 1 over x is part of that function. So 1 over x is base, and then I just get to shift everything 2 units down because it was subtracted. So I'm going to take this line that the function follows, and I'm going to put that line 2 units down, and I'm going to draw the same shape now, except now that shape, as you can see, goes down 2 units. So this new axis, right, the x-axis shifted 2 units down. I need to call that horizontal asymptote, but we don't get to talk about horizontal asymptotes until 2.6. So I'm just going to say that I'm shifting x-axis down 2 units, and I draw the same shape. I need you to see that the black line and this dashed line are the same shape lines. They're just on a different height, because the solid line, which is my solution to the problem, is the one that is shifted down 2 units. And that's it for shifting up and down. There's nothing else we need to say. You take the shape, whatever the shape you get from here, because again, right, we are learning forms. We are not learning particular examples. We are learning this concept for every function you will ever see if you end up going to graduate school for mathematics. You will still be learning new functions. And this applies the same to those functions that you learn in your PhD program, the same way as it applies to square root of x, which is algebra 1 function, right? So you are learning the concept, and the concept says when you have one of these vanilla functions, when you add number to it at the end, that function shifts up by that number, that many units. And if you subtract number at the end, that function drops down by that number of units. And you can see that in this example. 3 up because it was plus 3, 2 down because it was negative 2. That closes shift up and down. Now we move on to shift left, right. And this one is achieved by adding and subtracting value directly to x. So each x of your function has to have the same either plus 4 or minus 1 or whatever in order for that graph to shift. You can't just have one of the x's have plus 1 and the other x has nothing or has plus 4 or minus 13, whatever. That doesn't work. Every x of the function needs to be added or subtracted the same number. Now, when you add the value, you shift left. When you subtract a value, you shift right. Now, someone might say, no, wait, that's opposite. No, it's not. It's actually the shift up and down that it's opposite. Because technically, if you're looking at this, there is a y equal on this side. And see, this plus and minus c is actually added to y. It's not added to x, it's added to y. But when it goes to the other side, it will change signs. So it would be minus plus c, like this. So now you see that the minus c is actually shift up, and a plus c is shift down. You would still call that opposite, but that's just how mathematics works. So all of these shift formulas actually have a minus sign in there. It's very simple to verify those things. Just pick any function, compute numbers, right? The middle school method always works. So if I want to now shift my function f of x equals square root of x, right, which has the vanilla state like this, if I want to shift it, let's say, to the right, I need to subtract a number directly on x. So if I have f of x equals square root of x minus 2, then I am shifting my graph 2 units to the right because I subtracted 2. Minus 2 means right 2 units. And I'm just going to put little note over here on the side versus f of x equals square root of x minus 2, which is outside of the square root, in which case it goes down. We know that. That was the previous one. I just want to immediately give you the contrast of what the function looks like when you modify x directly and what the function looks like when you modify the entire function by adding or subtracting a number. So if you add and subtract number after the vanilla function is done and over, then that number would add and subtract, it would raise or lower the function, meaning shift up or shift down. But if you are impacting directly x and then the rest of the function happens, in that case you are shifting left and right. It's hard for some students to see this in the beginning, especially if you never paid attention to notation and you were sloppy and never learned notation. Of course, then it's going to create a lot of problems. But if you are really OCD with the notation, you will have no problems in this particular area. Let's take a look at another example. Let's say your g of x is absolute value of x. Okay, you know you just learned that, if you didn't know, that's the V-shaped graph like this, right? So that's the vanilla graph for absolute value of x. No one is asking why, so I'm just assuming you all know why, and I'm just moving along. So this is our vanilla graph for absolute x. And I can have g of x equal to x plus 3. So if I have that, so this is a direct left 3, because I am adding 3 to x, which means that the graph will shoot 3 units to the left. It still should look like a V, right? 45-degree angle on each one of the lines, because this is technically mx plus b with a slope 1. So, right, so you have this. But see, the thing is that, well, let's contrast right away. Versus g of x, which is going to be root x plus 3, in which case it goes up. So the thing over here is to be very careful what type of the notation, right, you have. Is this 3 modifying the entire function, in which case the thing goes up or down? Or is it modifying x, in which case it goes left and right? So that's one of the that's one of the problems. Now, the trick with the left and right shift is that if you have multiple x's in your function, it needs to subtract or add the same number to each x in order for it to shift for the intentional amount. If you use different values, obviously it's not going to work. Cool. Now, we get our combo number 1. It's like when you go to one of those garbage places for food and you order combo 1. Well, I'm going to order a combo number 1 right now. F of x is equal to square root of x plus 3 minus 1. There you go. Can you tell me what transformations you see in this particular problem?
Left 3, down 1.
Perfect. Left 3, down 1. All right. So now I combined those two together into the same problem. And you can get any combination, right? You can get left and up and right and down. You know, you can get all of them. So it's not learning the example. It's not learning the square root example. It is learning that when you add or subtract number on x, function goes left and right. When you add, subtract number on the entire function, it goes up and down. The shape of the line is governed by root x, x squared, linear, or whatever. So I want to set this up usually the way the exam is set up. See, exam gives you boxes and provides you, these boxes are, supposed to be the same size, and provides you with a line underneath to write. So you go and you say, aha, so this is my vanilla function. So my vanilla square root looks like this. So what I have in here is y equals root x. It's just a vanilla function, nothing special. Going to the next step, you wanna do left 3? Not a problem. We're going to draw our x and y, and you are going to say 1, 2, left 3, and you draw the same shape as you had before. So now what you have here is y equals square root of x plus 3. And now off of that graph, you work the next graph, which is down 1. So you already have your 1, 2, negative 3. All you need to do now is to put it down 1 unit and draw your graph from there. And there it is. So you actually build this graph one by one because you keep adding transformations. So on the exam, you get 6 boxes because you might have 4 or 5 transformations on it. We haven't covered reflections and stretching and all that stuff. So we are 1/3 into it. So every problem that you get has this kind of flow of staring at the problem to see what's the default parenting vanilla function, whatever you want to call it. Once you have that pinned down, you know what the shape of the graph you're going to use, and you always put the default or vanilla graph in your first box. And then you go and you say, okay, here are the transformations that are happening, and then you pick one transformation, you do it, then you get the second box, and then from the second box you work the third box. Don't reset and go back from here, because then you completely ignored one of the transformations. You are building up. So you start with the vanilla. Here's my first transformation, and then I'm keeping my first transformation. I'm adding one more transformation on top of that one. So that's that part. I'm going to put one problem with boxes for you to try it now. Unfortunately, I can't see what you have, so I'm just going to give you a minute or so to sketch the stuff in boxes, and then I'm going to work out the problem. So y, or f of x, or whatever, doesn't matter, is equal to x plus 2 squared minus 4. So no pressure. You have 18 seconds. Go.
What did you want us to do once we finished graphing it?
Reflect upon it.
Oh.
Yes, meditate in that area. think think about what else I could twist, right? Think about what if +2 and -4 was switch locations. Like there are a lot of things that you can you know you can do to kind of further up thinking about this problem. So now I'm going to, since you you know mentioned it that it went well, let's take a look at uh, the problem and the solution. Okay, so we start again with, since we are going to have two transformations, we first list those transformations, and those are two where?
Two left.
Left and 4
Down.
down. Awesome. 2 left and 4 down. So now I'm going to put the box for my vanilla, box for first, and box for second. These are all perfect rectangles. It's just your eyes are crooked, and you should check those out because clearly you don't see well. There we go. So this is my vanilla. I'm going to call that y = x squared. Then I'm going to go to left. Okay, that's not going to be a problem. 1, 2, so vertex shifts 2, and I keep the shape. It's still the U shape. We call that parabola, right? And it's at -2. And now I'm going to call that y = x + 2 squared, shifted left. And then I need to shift 4 down. So now I keep my -2, but I also go 1, 2, 3, -4. So now those create a point, and then the graph. That's the final graph. You label this point as -2, -4, and you're done. So y = x + 2 squared minus 4. So all these numbers are doing are shifting left, right, up, and down. Good. Now we are going to take a look at the they're called vertical and horizontal shift, right? Words, vertical and horizontal. All right, the next set of transformations are reflections. You're thinking immediately mirror for the vertical, and let's say a surface of the water, or you put mirror on the floor, and then right you have the other reflection. So reflections now. And those are very easy, because all you need to do is to put a minus sign on the entire function, or the minus sign on each x. Again, right, you remember how you added the number to the whole function and something happened? Well, now you are going to put the minus for the whole function to reflect, and then you're also going to put the minus sign on the x only, and it's going to reflect again. All right, so how these reflections work? Well, the reflection is going to be this way. Come on, there we go. Come on, tablet, you can do it. That's it. So first reflection that I want to have is this reflection, f of -x, and that is reflection on y-axis. This means that your y-axis literally behaves as a mirror, because it has the depth of field and everything, and the function will expand in that direction, in the opposite direction of what it did originally. Reflection is done on y-axis, So if there is a space in between the y-axis and the function, that space will also exist in the reflection. You know that when you make a step forward or a step backwards in front of the mirror, the image of you also makes a step. So the distance between you and the mirror is also the distance in between the mirror and your imaginary image inside the mirror. It's the same distance. So now, immediately jump into example. There's not much here to say. You all know the way the mirror works, right? So when you take a look at the, let's say, f of x equals square root of x, you have your vanilla function, and you can see that the domain here are all positive numbers. You can only plug in positive numbers. And you plug in 1, you get 1 back. You plug in 2, you get 1.41, and so on, right? So you can calculate, but you can't put -7, because if you use -7 doesn't have a function to bounce off of into y to give you the number, to give you the answer. So negative numbers are excluded from, right, the domain, and you cannot be computed in square root of x function. However, if you reflect that function on the y-axis, then the positive numbers end up being the ones that are not welcomed. And this is your reflected square root of x. Now, does this work? Hell yes. Because now, -4 is a good input. Let's take a look. What is the f of -4? It is square root of -4, which is square root of 4, which is 2. I got my 2 over here for that. So those are some ideas, right, that you can explore now when you, right, you can also play the game with the domain. Let's take a look at some functions, reflecting them on the on the y-axis is completely unnecessary, right? For some functions, that's completely unnecessary. Think about the function f of x equals x squared. Come on, tablet. Thank you. Well, when you draw x squared, or you graph x squared, whatever, would it really have any impact if I just reflected it? Well, if I reflect, then just the points swap from left to right, you get the same graph. You don't get a different graph, you get the same graph back. Now, would algebra prove that? Well, yes, because it's an even function. If I replace each x with a negative x, and I apply the square, I still get back my good old x squared. So it's pointless to reflect x squared, because you get the same graph back. Absolute value is another one. It's that v. And if you reflect v, right, if you reflect this graph, then the left branch will go to the right branch will go to the left, but they will look the same. So once the transformation is done, you still can't tell that anything happened. And you can again confirm that through basic algebra, because f of -x is equal to absolute -x, and absolute value just kills that negative. There you go. It's still the same function. So there are some functions that, when reflected, stay unchanged, right? We will learn later cosine graph from trig will have this property. when you reflect it, because it's even function. When you reflect it, it will be the same function. So reflection on the y-axis is achieved by placing in the negative sign in front of x, which is why, right, we have this as a definition of reflection on y-axis. Now, reflection on x-axis clearly is going to have a minus in front of everything. First of all, right, it's the -1, right, times -1 that makes reflections possible. So I hope you are slowly catching on to the pattern that the first two, which were horizontal and vertical shift, they were both adding and subtracting numbers. One did that to a function, the other one did it to x. Now you have the same deal here. You are reflecting with a negative sign, -1. But if you reflect the entire function, it's going to be flipped on the x-axis, reflection on x-axis. So, reflection on x-axis. Now, I always like to start with the square root problem, but there are, technically, you can use any other function. We'll use x squared as well. So if I start with f of x equals square root of x, again, I have my vanilla function that looks like something like that. That's terrible, but okay, that's better. So that's my square root vanilla function. Now I want to come up with the negative f of x, which is negative root x. Well, hopefully you see that you are not messing with the input now, you are messing with the output. It's that negative in front of the root x that can jump on the other side, right, and divide or multiply whatever the solution. So you actually switch all of the y value signs effectively. That's what this does. Now, what would the graph for this look like? Well, come on, it's a reflection on x-axis. How hard can it be? Right? That's all it is. It's reflected on x. So x acts as a mirror, and then something that was here before is now just going to be below. That's what the reflections are for. It's not as useful as the previous one, because the previous one switches the domain, right? But, you know, here and there you're going to run into an application. Sooner or later, you have to. Another one. Now, this is the one you know, actually. The x squared. F of x equals x squared. That's your good old friend parabola opening up. But then, if you change this, now, oh, the minus is on the outside. So the minus and then x squared. We don't need these parentheses, but I'm just going to put them there. You see that your x squared computes the same y values as before, and then this minus flips them down. Because if your calculation was 3 squared, then that 3 squared is 9, and then there is a minus sign in front. So that's a positive value, which is why the graph looks up. But then this negative in front flips that graph upside down. So now this is your graph for the quadratic function that it's shifted. Sorry, that it's not shifted, that it's reflected on x-axis. Questions, concerns, you're always welcome to jump in. and say, whoa, 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 I didn't get this, didn't get that, whatever. Questions, concerns?
I have a question.
Sure.
I know I was never good at this topic even in high school, so I'm just trying to make sure I guess I'm understanding it correct. So when it's a reflection on the y-axis, your original x values change, and then if it's a reflection on the x-axis, then the y values change.
Very good. But they are changing by taking on the minus sign. They are not changing, because if you add and subtract numbers, you are shifting graphs left and right.
Yeah.
The change that you are picking up here are the negative, it's times -1. So if you look at this formula, this is your good old function here, and then times -1 to flip it. So the
Oh,
negative signs flip functions.
I see. Okay. I just get confused with like different y values and different x values for each of the functions.
Well, I'm not sure what you mean.
No, I
Why?
now, but before I used to get confused between the
Okay,
two.
so but it makes sense now. That's
Yeah,
that's
it makes
that's the bottom. Awesome. Woohoo. Now, ready
I
for
have a quick question. I think
Yes.
I know the answer. I think it's pretty simple. But to get that function negative f of x, equals negative x squared, to flip that back into the original parabola, you would just multiply the whole function by -1, right?
Again,
You would
yes,
yeah, you do it again.
because the flip of a flip is the original location, right?
Gotcha. Okay. Just wanted to double check.
Awesome. Right. In general, you only do one of these. I mean, why would you flip it and flip it back? But you are 100% correct. Yes. All right. Combo 2. Combo 2 says, can I just shift and flip at the same time? Yeah. I mean, you're going to do one, then the other. You're not going to do it at the same time. But now we can combine transformations of function, meaning shifting them left, right, up, and down, so horizontal and vertical shifts. We can combine that with reflections. So now we can go and find a problem which says sketch the graph of f of x, where f of x is given as negative square root of x plus 3 and everything minus 1. So how many transformations do we see in this particular case?
3.
3. Awesome. So we see this -1. That -1 is what? What kind of transformation?
Reflects on the x-axis.
The -1.
Oh, sorry. No, that goes down 1.
Down 1. Awesome. Down 1. Now you have the plus 3. What would plus 3 do?
It's left 3.
Mm-hmm. Very good. And then we have this negative in front of the square root.
X-axis reflection.
Yes. So I'm just going to call it flip x. Flip x. All right. So I got to have a default box and then 3 transformations. So that's going to be 4 boxes. Okay, let's put 4 boxes. You don't have to do the boxes. You can just draw the graphs, but
Does the order you do the transformations in matter? Like, for example, could you flip both?
nice. That's what we are going to discover now.
Gotcha.
All
Is there
right.
like an order of operations for transformations?
Order of transformations, right?
No, that makes sense.
Order of transformations. Yes, good. So the answer to that question is no. There is no order. However, there is an easier way to get to the problem every time. So if I say, you must do this, no, you don't. It just makes it easier. And I'll write it here in blood. Reflections first, please. With this weird nuclear E at the end, whatever. Reflections first. And the reason why reflections first is because of that distance that I talked about before. See, it is really hard to reflect the problem once you shifted left, right, up and down. And a lot of students get their grades massacred by this because they don't pay attention to this friendly suggestion, okay? Even though I'm screaming into the screen and the microphone, right? So the proper way to do this problem is to say, oh, the vanilla function is the square root. X, y equals root x. That's my vanilla state. Now, flip on x-axis first. This is what the red writing said. Okay, we can do that. Here's my flip on x-axis, and the function now goes down. Now this is y equals negative root x. Now you can pick down 1 or left 3, it doesn't matter. But the reflection done first is really important. It makes your life easier. So I'm going to shift down 1. We say down 1 and then left 3, yeah. So now we go down 1. And this is going to be y equals negative square root minus 1. That's okay, right? You are one step away from the end. All I need to do is left 3. Now, to do left 3, I have to keep my 1 and go 1, 2, 3 and keep the shape. Now, on exams, you are responsible to write the coordinates of these floating points, the minimum, maximum, like a vertex for parabolas, and then this square root, right? This origin point, right, from which the square root function emerges, right? That's the one where you start, and we are done. Y equals negative square root x plus 3 because we shifted left, and then minus 1 because we went down. So this picture represents that. Now, there is a website called Desmos, and you should use that website to verify these and see if you learned properly. You can also use graphing calculator or whatever makes you happy. There are many websites that you can use for graphing, not just that one. There are also dedicated apps in the App Store. So I think it's the second most popular after Candy Crush. So it's the math graphing app. No, it's not. I know. Relax. Reflections first, please. So that was the problem that combined this. One more type of transformation. Stretching and shrinking.
Does that add to the order we do it in, or does that not matter? Oh, okay.
reflections are still first. And
Yeah, I figured.
yeah, reflections are first. That's, I mean, I wrote it in this um, this huge billboard over here says reflections first. So even though we didn't cover stretching and shrinking, it's still reflections first. So stretching and shrinking, you're just making your functions taller or shorter, or you make them fatter or skinnier, right? Um, the best function to use to explain this is trigonometric function sine x or cosine x. So I am going to use that, even though we're going to learn them all the way, in like 2 months or so. I'm going to still use sine x because it's just, and I think the book uses the same without actually telling you what it is, which is why I am so much better than the book, right? Haha. Anyway, stretching and shrinking happens when you multiply function by a value or each x by a value. So we are going to now define the vertical one, and that's going to be c times f of x. So vertical stretching and shrinking. So how does this work? Well, come on, f of x is a y value. When you multiply it by a number that is bigger than 1, it grows. When you multiply it by a value between 0 and 1, you shrink it. Does that make sense? Well, hopefully it does, because 3 times 4 is 12. 1/2 times 4 is 2. So when I took this y value, let's say, of 4, which is your f of x value, remember each f of x is like some y value computed eventually. So if that y value is 4, if I am multiplying that y value with 3, well, I just made that 4 larger. I made it 12. But if I multiply it with 1/2, I shrink 4 by 2 into 2. So how does that reflect on functions? Well, we can't really do I mean, we can with the square root function, but pretty much every other function is terrible that we know of now. So I could use the square root function for vertical, but the sine function is still better and I'm still going to use it. Let's go with f of x equals square root of x, and I'm going to draw that here, but I'm actually going to do the OCD here and use the actual points. So because I want to draw this graph as precisely as possible given situation. So we know 1, 1, and then square root of 4 is 2, 5, 6, 7, 8, 9, and square root of 9 is 3. So this is the quote-unquote exact graph for square root of x, because it hits all of the points 0, 0, 1, 1, 4, 2, square root of 4 is 2, square root of 9 is 3. I didn't go further. I could have gone with 16 and so on, but whatever. So this is my vanilla state. Now I want to add to this and say, how about if g of x is 2 times root x? Aha, 2 times root x. So each one of the y values, because these are the y values we got, that's how you compute them. You plug in 1 and square root of 1 is 1. That 1 that you got as the answer is the y value. You see that each answer is multiplied by 2. So all I need to do here is to say 1 times 2 is 2, 2 times 2 is 4, and 3 times 2 is 6. Right? Since My original y value was 3. When I took square root of 9, I got 3. Now I need to take that 3 and multiply by 2, and 0 still stays 0. So now this puppy here is 2 root x. So every y value, even those that I did not compute, every single y value was multiplied by 2. And I have this graph. Now I'm going to draw one more. How about if I go age of x is equal to, I don't know, 1/3 root x. You can also say root x over 3. Whatever, right? Depends on your algebra competence. Well, what this does is just takes my old answers and divides them by 3. So instead of 1, I get 1/3. Instead of 2, I get 2/3. No, 1/3, sorry, because I'm dividing 2. No, I was right, 2/3. And then this becomes, when I divide 3 by 3, it becomes 1. Wait, I messed this up. No, I was right. It was 1/3 over here. There we go. So now this one is tiny. It's still a square root, but this one is divided by 3. So there you have it.
So vertical stretching is just manipulating
The
the function through multiplication, or
Yes.
the y-axis through multiplication.
Yes, manipulates it through, yes, and it's, if you are hopefully see that you are manipulating the height of it. Now, the best way to understand, even though you did not, I mean, some of you might have studied trigonometry, basic trig or something in high school. I mean, you all should have to at some point. Maybe you didn't pay attention or whatever, but y equal sine x is a wave function that literally looks like a wave. So I'm just going to put these dots that will help me draw this thing. There we go. It drops down, it comes back up. So this is one of the bumps of the sine function. It goes infinitely in both directions, but that's for our chapter 4. So hold your horses, okay? If you have horses. If you don't have horses, hold whatever you have. So this is your sine function. Now, I need you to understand that this could be the wave on the surface of the water, right? When you look sideways, this is what you see. This is also an earthquake, sound waves, right? It's all the sine. Also, any oscillating body, like a pendulum rocking back and forth, and a spring, having something bounce on a spring all the time. And now we can go into electrical engineering and so on, talk about oscillators and things like that for electrical purposes, for electrical engineering purposes, but we don't have to go into any of that. Waves are the best. What do you have? You have a ship, right? That should not face the wave straight on like that, because these waves are traveling in time. But see, if I go and I say y equal 2 sine x, which is exactly what we have, 2 f of x, because the old f of x is just sine, and then now you're multiplying it by 2, you just have your, what you just did is you made this so much worse. See, now these waves are much larger. The wave, let's say, used to be 2 meters over here, which is 6 feet. And the trough over here was also 2 meters for a separation of 4 meters top to bottom. When you multiply this by 2, this one jumps up to 4 meters height and 4 meters over here, making a distance of 8 meters. in right, which kind of makes sense because the 2 meters, right, made a 4, and then these 4 meters made 8. But the idea here is that, yeah, all of a sudden from here to here, right, you are having much larger height. And that's achieved simply in mathematics. It's so easy to understand anything technically. Someone talks about the waves and the height of the wave, and I'm only thinking about, yeah, amplitude of the sine function, and then I can multiply or divide by any number. Can I make this skinnier? Of course I can. G of x is equal to 1/2 f of x, which is 1/2 sine x. I don't care. See, we shouldn't be caring what function you're plugging in here. I'm talking about the function you're not supposed to know anything about, because you're supposed to learn about that function in this class, but 2 months in the future. And what do you get? You say, oh, I just need to take each one of my numbers and cut it in half and just draw the line, and I don't really care, right? I don't really care. I will never forget my Calc 1 professor who always assigned some functions you never seen, right? Just to make it clear that no one cares what the function is, right? It's the principle that you learn that applies to all functions. And your job is not to now sit down and go in a book ahead to learn all you can learn about sine. No. The only thing you have to realize here is that, oh, I have some kind of function, then I made it twice as large, and the graph was twice as large, and I make it half, right, as small, and then, right, the graph shrunk. So technically, that's it. The same thing is for horizontal, right? So we also have a horizontal. Stretch shrink. And that's going to be when you multiply x value by it. And now this is going to, now this one is something that you really need trig to see. So we're going to go back to our good old friend sine function, even though you don't know about it yet. And I'm going to do this. We're still going to go 2, 2, 2, 2, rise, fall, rise. There we go. So that's my sine function. And what I'm going to do is I'm going to now for, let's go orange, I'm going to say g of x equals sine 2x. So I took this x and I multiplied it by 2. That's exactly what you have up there in the notation. You are multiplying each x of the function with some number. And I decided for that number to be 2. What you have done is you made the function 2 times faster. That's what you did. You made the function twice as fast. So you go and you say, every single one of these points is going to move in halfway, and my function is going to rise, fall, and rise in half of the distance.
Oh, so it's like when we were shifting earlier where it's opposite, or like it looks like it should be opposite.
Okay, if you want to say that, but
Because even though we're multiplying by 2, it's getting smaller.
true, but let me tell you that if you drive faster, you get somewhere quicker, right? The time goes down. So you can look at it. I mean, if that's the way you understand it and see it, that's perfect. It's not wrong, right? I'm just offering you also alternative way of seeing it. because I spoke about being faster, meaning that the whole squiggle for this function is going to end sooner, because when I say 2x, I can just fit another one over here and have two of them, have two loops. It's called a period.
Gotcha.
So now you're looking at this and think, what possibly this could be used for? Visible light? Literally, the difference between black and orange curve is the difference in the wavelength. So if you heard about the wavelengths for colors, which you can now write down and then research later, you will see that because the light travels in the wave and the wave is portrayed this way, then the how fast the wave moves, right? And that's literally determined by this number in front of x inside. Well, it's t actually in the physics equation, but whether we say 2x or 2t, who cares? So all of these things will find their way into your physics and your engineering courses down the line. You need to know how to shift and shrink. Oh, I did not hold on. I did not make it slow. Slow. That means that this point is 2 times slower. This point is here. The other point is 4 away. 2, 3, 1, 2, 3, 4. Then 1, 2, 3. It's not even going to fit. It goes wee, right? So you can also think of the accordion, that musical instrument, if you know what it is, right? So stretch it, shrink it, stretch it, shrink it. You can also think of a spring, right? That you can compress and points out. So this ends all 6 different formulas, similar formulas, which do transformations, meaning you have left and right, up and down shifts, you have reflections, and now you have a stretch and a shrink. Now, this is the time when you get to learn something actually. You have your f of x plus minus c. You had your f of x plus minus c. You had your f of negative x. Let's do negative f of x and do f of negative x. And then you had your c times f of x. And finally, f of c of x. What do you see as a pattern on this list?
You're either doing something to the x or the whole function.
Every single one is only operating on the x or the whole function. If you see that, you guys are done. If you see that here, here, and here, you have your function intact, and extra bells and whistles are bothering the function. And here, here, and here, x is being directly bothered, not the function on its whole. So when I say on the top, square root of x plus 3, square root of x plus 3, negative square root of x, square root of negative x, 3 times root x, and square root of 3x. You have to be able to pick these things up for every type of the function, not just the square root, which is the one that I wrote here. Because, as I said, in Calculus 2, you learn hyperbolic functions. So the same rules apply. You are not learning this for the 6 functions you know, if you know those 6 functions that I listed at the beginning of the lecture. You are learning the principle for every function you will ever see in your life from this point on. PhD level. There's also after PhD, it's called postdoctoral degree. So you can have a couple of those. Every single function that you
I have a question.
possibly imagine will have these properties. Yes?
With stretching and shrinking, it's the opposite for vertical and horizontal, like multiply versus divide. Do I have that right?
Depends on if you are using the square root. Oh, actually, yeah, the way you ask the question, yes.
Okay.
So it is the opposite. Now, I kind of try to stay away from those generalizations. It's not that it's going to get you to do something wrong at one point, but I don't know, memorizing way too many rules for me obviously was a problem in the past, which is why I could never do organic chemistry or biology, because you have to memorize a lot of stuff, and I hate that. The way I look at these formulas is always what is going to happen with the function. And see, when I keep multiplying, that's why I explained this one here with the wave. You multiply it and you make the wave bigger, because when we learned y equals f of x on the first day, when I say c of f of x, I'm also saying cy at the same time, because y is f of x. So if I have 3x squared, I just know that the vanilla x squared has some values in that chart of numbers, right, of values, and then the 3x squared will will have the same x's. Each y would be times 3, which means I'm making that x squared taller, right? Making that x squared taller, because each point moved 3 times up. So, and the way I learned this is I actually did my self-discovery on the square paper using 100% of OCD that I have been gifted, right? Through generations of engineers and people in the past. I go and I say f of x is x squared. And then I say my orange g of x, and this is how you actually learn these things, 2x squared. So I draw the black and the orange on the same one. Now, if you do this on a calculator or the software, you're just wasting time, because you're not going to learn anything from it. You have to do this by hand. You have to hate every second of it, right, to get to appreciate the entire picture. So you go and you say, all right, there's my chart over here. I got my x values, then I got my f's and my g's. So for x values, -1, 0, 1, and 2, let's say. And now let's calculate my f's. -1 squared is 1, 0, 1, and 4. Aha. 0, 0, 1 and 1, -1, -1, 2 and 4, 2 and 4, and that's going to be 3 and 9, so 5, 6, 7, 8, 9, and a 3 and symmetric 1 on the other side. There we go. So the black function, right, the f of x, is this puppy right here. Now, where's my g? Well, g said take the original black function and multiply every y value by 2. 2028. So -1, 2 0, 0, 1, 2, and 2, 8, which will have a symmetric one on this side. So now when you do this, you see that for every x, right, if you draw a vertical line anywhere, you draw a vertical line anywhere, literally. You see that every time the orange function y value is taller than the black y value for every single case. And look at it does tell you that the orange is twice as tall as the black, except at 0, 0, because 0 times 2 is still 0. But at every other point of this graph, the orange is going to be twice as tall as the black one. And
so then,
yes, go ahead.
Then your new points become X and G instead of X and F?
Yes, all of these are y values, and it's always x comma y, but this y here is computed from f, and the other y is computed from g. Because remember, y equals f of x, but also y equals g of x, right? Because the point is always x comma y. So some of these y values, the black y values, are computed with f's, and the orange y values are computed with g's. So that's why we
What does G
label on
stand
the
for?
graph. Yes.
What does G stand for? I know F stands for function.
G stands for function as well. It's just to differentiate from F. So you're going to have f of x, g of x, age of x, and then later on we're going to talk population.
So it's just a new variable?
It's just a new function because these two functions are not the same, right? They're
Yeah.
not the same function. So I'm going to call one function f and another function I'm going to call g, just because
Gotcha.
they're not the same function.
Gotcha.
So G is the transformation of F.
Yes, yes.
Okay.
And G is a transformation in the sense that it had a vertical stretch. Now, are you able to absorb a mind-breaking revelation here? Can you withstand this now?
Yeah.
All right, I hope you're all sitting down. So we all see when I draw the vertical line, we all see the vertical stretch, because we all have seen that every single orange point is 2 times taller than the black point, right? We all see that. Do we?
Yeah.
Yeah.
Yes.
Cool. Do we also see a horizontal shrink at the same time? The orange function is skinnier than the black one. Or the black one is fatter, whatever way you want to. Do we all see that? And it happened at the same time. We stretch it on one way, we shrink it on the other. What the hell just happened? Can we get some algebra voodoo over here that will actually show that that's the case? And the answer is yeah. So what we experienced was the f of x equal x squared, and then my g of x equals 2, and I'll put the black x squared, because that's actually your original x squared function. And you know that this 2 is making it taller. But now I need to do something here so that I can also make it to shrink it. And if I just rewrite this 2 as a square root of 2 squared x squared and combine this into a single parenthesis, everything squared, all of a sudden, what used to be cf of x becomes f of cx. Welcome to the Twilight Zone. So now we see that this particular transformation we did is not just messing with the height of the function, it's also messing with the width of the function. right? Ooh, there's a lot more for you to think about than just, oh, these are the basic 6 transformations. These stretches and shrinks, they're nasty creatures, right? On a sine and cosine functions, they just shrink or stretch one way or another. But for other functions, as you can see, like x squared here, they actually not just stretch one way, but they also shrink the other way. And that is something that you guys can, look into once you understand the basic, right? Because this is going to be your when you level up your character to level 70 with the previous knowledge, then you tackle level 71 over here. So I don't want you to sit now and try to figure this out, because you won't. You won't figure this out until you have clear understanding of everything we did before we got to this point here. Mathematics always builds up, and then there's always another next thing that you can slap on top of what you had before. So visually, if I never gave you any of this stuff here, you have nothing. You're just looking at the graph. And if I ask you, what is the transformation done? Half of the classroom is going to say it was stretched vertically, and other half of this classroom is going to say, oh, it was shrunk horizontally. And both groups are correct. Both groups are correct. It's just the way your brain is wired to see one before the other. But both of them happened at the same time, and algebra did prove that there is equivalence between this one and this one for this particular function. And as I said, that doesn't work for sine x. So you cannot learn this case by case. You have to say, okay, well, algebra would work this way in this case and would not work, in the other case, and so on. So I'm just going to put this in a box. Oops. I'm going to put this in a box on a side and not bother anyone with it for now. But if you are truly learning these things because you know you're going to need it eventually, you will come back to this box once you are done with your homework, once you understand all of the concepts that we talked about in this particular lecture. Then you're going to go and you're going to bend your mind, and then you're going to ask yourself, is the same thing happening with my absolute value? Is the same thing happening with root x? Is the same thing happening? And then you might remember in 2 months, if I don't remind you, does this happening with a tangent graph or a cosecant graph or something like that? Because I remember a professor said it's not going to work on sine and cosine. But again, where it works and where it does not work is going to be the question, right? And the nastiest one to understand of all of them is the linear line. It's supposed to be the easiest function, yet it makes the largest mess when you try to do reflections on it. Because literally everything for linear function, each one of these reflections can be flipped to be another one of them. Transformations, not reflections only. All 6 transformations on a linear. So once you get to level 71 over here, right, when you level up your character all the way to the end, you're done with the homework and you know everything. Try to untangle linear function and see what kind of horrors, because you are going to see that every single transformation you do for linear function, right, you add a number and you shift up, but you also shift to the left, and you go, what? At the same time. And these are the things that for linear function, you can look at the same transformation from 2 different angles, just like we could have looked at it here as the vertical stretch but horizontal shrink at the same time. You pick one of those, you don't have to do both, right? But the situation is, because I did have students that really invest their time and try to break their brain over this, come to my office hours and ask, Professor, is this a vertical stretch or horizontal shrink? And I say it's both. and I can see the cogs moving in the brain trying to put all of the stuff together. It's really interesting, but learn the basics first. So now you have the tools. Probably the most important thing out of everything I wrote in the last hour and a half is right here in this chart, where you pick up the patterns and you see that every other line is something is done to the entire function, and then every other line with blue arrows, something is done to x directly. And you have the examples on the side of the square root of x function, where you can pick out vanilla square root of x unchanged, right, in its natural form, in those lines where the you also have highlighted f of x, that it's not changed or anything, so in its natural vanilla state. So I hope that you guys will study this, and if you need to watch this again, obviously it's available on YouTube, so you can go and watch this 15 times if you need to, but it is something that will never go away. You know, especially in schools that do not allow calculators, and also calculators just make you slow. I will explain that at some other point, but calculators by default always make you slow. And in some cases, you have to make quick decisions, and no one cares that you have the answer to the 6th decimal when the approximated answer came in a couple of seconds faster than yours. You will always be the second in that race. So we'll talk about those concepts as we go along. That's it.